suppose you are so tired, but be patient for 1 hour. Okay, so in this lectures, I would like to talk about chemical system, not biological one. And the title is Interaction of Travel and Sport, but the motivation is coming from the billiard problem of a self-driven ball for far from equal state. Of course, I will explain this meaning, but a billiard problem is very popular. So maybe I hope you may enjoy. Okay. And then, so this is just a standard, the billiard. Of course, maybe someone already play billiard. Okay. And this guy, this is the dog. Okay. This also, I don't know he or she, he played billiard. I can show you. So maybe he is much better than you. Okay, so this is a sort of the dog really enjoys playing and billiard. And also nowadays in some universities they develop a sort of robot. So this robot also plays very good billiard. And then this is a sort of self-driven robot plays billiard by moving, just moving and hit so something like this. This is also very enjoyable. And today, so I would like to introduce a kind of a billiard which plays by a self-driven chemical ball, so like this. This is just moving by itself, okay? And then just reflection. And moving here and moving like this. This, the billiard which I would like to introduce to you in this lecture. So this is sort of the billiard problem of the self-driven ball, okay? And what kind of materials? I told you this is a chemical system. So this is a chemical system is a camphor. Do you know this camphor? Camphor is a kind of very strong smell, and most ball for insect. Usually, so when I was when a baby, I suppose, this camphor put in the dressing, the box here, so that protect from the insect. Okay. So this is and then this is trees, and you can get a sort of powder of camphor. Okay. And this is very typical, the phenomena, just camphor scrap, put on the water, and it is floating, so like this. And then just this is, here from the top, okay? So this is just moving here, and also so rotating here, and coming here, and deflection, and moving here, so something like this, okay? So it means this is time. This is time. So here is just rotating like here, and go down, and up, and rotating, and moving this way, and rotating. So something like that. Okay. So this is so-called camphor dancing. Okay. Why camphor scrapping can move? Okay, this is just this is a camphor boat, and it is a very nice toy for the kids. Just this water, okay, and this is just plastic plate with the shape of boat, and you put the scrap here, and put on the water, so that's the swimming. Just moving. Yeah, this is so-called camphor boat. Okay. Okay, and why this camphor boat move? Okay, this is there two phenomena. One is just sublimation here, also dissolution here. And because of this resolution, so surface tension around here change depending on the concentration of camphor, dissolution camphor, like this. And then some Japanese chemists, that check the dependency of surface tension on the concentration. Okay, this is sort of monotone decreasing, and due to the unbalance. Okay, due to the imbalance in this area and this area, they move. Okay. Okay. So this is very rough sketch. This is dissolution. Okay, and the camphor dissolution, and then there is some difference of the surface tension in the front and also back. Okay, so this is sort of chemical energy, and then this movement by some convection. Okay, so this is just the transform from the chemical energy to the kinetic energy, and just the motion also. Okay, so this is sort of artificial motor, no heating. Okay, the same temperature. Okay, but moving like this. But it's very similar to the some engine. So we just fuel just like this dissolution and just moving so like this. Okay. Okay, so this is a kind of previous earlier result. What I'm interested in this phenomenon from mathematics. Okay, what does it mean, mathematics? So, the question in my lecture: if the camphor is uniform and of disc shape, just symmetric, okay, and also very uniform, okay, and put on the water. So the question, does it move or stay? Okay? So, how about your answer? And I suppose if you are mathematicians, maybe you may say the camphor disk may not move because it is uniform and rather symmetric. So we keep some symmetricity. That's why we cannot move. So like this. But if you are not mathematician but say the explained people, is it impossible to make a uniform and circular disk? Okay, so it must move. Okay, so what is right and what is wrong? Okay, that's my question. Okay, so in order to answer this problem, let us do experiment. Okay. Honestly speaking, I didn't experiment. That my student, undergrad student, he of course he is in the department of mathematics, but he didn't like to do mathematics. Okay, he preferred to do experiments. Okay, so this is sort of powder. Okay, and this is compressor. Okay, and put in the powder is like this. And so it's a sort of pressure. Then you can make a sort of the disc shaped camphor. And this is very thin. So this is, this is just 1.35 centimeter. And this wide is very thin, 0.05. Very light. But maybe so, at first, maybe almost 2 weeks. We couldn't make it. It's usually broken. Then maybe yes. Okay. This one is just sort of polished very. Then we could succeed. But anyway, so this is our disc. Okay, camphor disc, very small one and very light. That's important. Okay, and then put on here. And this is camera. And taken here, and put in here. So this is just brown. Okay, and okay. So this is very simple. So even mathematician can do that. Okay. So now let's do experiment. Okay. Put here. Yes, it moves because like this. Okay, of course, I can explain later, but definitely move according to our experiments. Okay, so observation is at first also usually this is just melting of course. So change the shape, but in a few hours, same shape, few hours. But finally, it's a sort of like this and disappear. Okay, so a camphor disk certainly moves, yes. And then the disk moves straight forward with almost constant velocity, And when the disk approaches the wall, it reflects before a collision. Sorry, this collision, as if it was an elastic particle. Okay, this is just observation. Okay, why? This intuitive argument the following. Okay, suppose this 1D case. Okay, and suppose this is a camphor disk, and this is a dissolved camphor. Okay, here, okay, and this concentration. And suppose this is moving. Suppose then after that this is fresh water. Okay, that's why this is much more larger than this one. That's why we can have a difference between the surface tension back and front. That's why in this case this is moving this way. Okay. Then if this close to the wall here, so you can see this blue one is like this. So here is a sort of the higher concentration. That's why this is moving this way here. So this is a kind of intuitive, the understanding. Okay. So moving here and all come back. Okay. Okay. And also if we put 2, then you can see a sort of a very nice reflection like this. Okay, so reflection 2 moving disk. So how about this case? This case is we lose the purity. In the previous purity 100%. Okay, but we mix in the camphor powder and cornstarch. I don't know, maybe you understand cornstarch. Yes, a mixing, and this is 1/4. Okay. So purity is very low. So what happened? And same shape, of course, and same width, and also same vessel, of course. Put here same huh? Doesn't move. Okay. So the answer is yes or no, depending on the purity. Okay. And then, camphor disk stops. Okay. And this is a very, very rough. The dependence of purity on the on a disk movement. So this is purity, and this is average velocity. Okay. So in this area, so very low purity doesn't move, and here it's moving. Okay, and the velocity also increasing. Okay. This is only 4, but this is a kind of the typical phenomena. Okay, so the answer is yes or no, depending on the purity. This is correct. And when the camphor purity is 100%, then we have this kind of the reflection property, and yes. So suppose this is the incident angle, the reflection angle. So this point is the sort of relation between the two angles. Okay. then usually, the angle relation is coming here. So roughly speaking, reflection is not perfect error. Perfect error is just on this line, of course, same angle. But in this is here. So it means, suppose here, okay. So it means incidental angle is bigger than reflection. It means this is bigger than this one, okay. This is also observation, no mathematics, okay. So that means this ball is not usual elastic ball. It's not usual billiard problem. Okay. Okay. So now, a compact disc behaves as if it were a self-driven ball and possesses a diffraction property. So now let us play a billiard of a compact disc by using mathematical model. Okay. This is second stage. And then this is done by Shifu Chen and also one of my former students, A. And then so we propose some model and also analysis. So maybe, model and analysis, okay. Okay, so this is our compact disc, okay. And two properties occurs. One is the sublimation, the other is the dissolution, okay. I told you before. Okay, so this is the model. At first, this scale domain is omega. This is the vessel domain of water. And omega t is here. This is a compact disc with radius r. This is just disk, okay. And we don't, we assume this shape doesn't change independent of t, okay. And the C of Tx is the concentration of dissolved camphor on the water surface, okay. And so this is an equation for the concentration of dissolved camphor. So this part is a sort of continuity equation. This is flux, okay. And this is a sublimation, okay, with rate Q here. And what it is, this is the sort of purity, okay. So, and if this S size becomes low, so it means the low purity, okay. And this is just a supply, okay, because from this one is just dissolution curve. So this is just X belongs to omega t, of course. And other region is just 0. Okay, so this is just, that this is sublimation, this is the dissolution, okay. Okay? And how about zeta t? Zeta t is the center location of the camphor disc. So I told you, we assume the camphor, the shape doesn't change. Only this center is moving. Then we know the location. So, and then this is the acceleration. And rho x is the density of the disk, and the pi r square h. This is volume, okay. So this volume, this is density, this mass. Okay. So this is force, okay. And that force is given by two factors. One is a molecular effect. This is viscosity. And the molecular is given, this is surface by the surface tension, okay. And this is viscosity in the water, okay. So this is a first step, okay. And then, and the molecular is given by the following. So gamma c is this surface tension, we integral, okay. So along this one, okay. Okay, and the gamma c is the surface tension, we know this one. I put him here, okay. And this is viscosity. Viscosity just this is the velocity. Of course, you know this is velocity and this is area. That gives the the viscosity. Okay. So this is, we know that these are two the factors, and so this is sort of balance equation. Okay. And we assume the following. Okay, at first, we assume, this is really mathematical assume, or simplification of model. We assume that a disk moves very, very slowly, such that acceleration is neglected. So something like this, okay? Then, this is 0. So this must be balanced. And this given by, this one here, minus like that. So this is equal. Oh, no, sorry. This plus, this and this plus equals 0. So this is this equal this one, okay? So it means like this, okay? So this is a sort of the equation for motion of comfort disk by using the t. And how about v? And in this setting, we assume the v is given by the gradient of kc. Okay, this is okay. So if this is like this, so moving this way, velocity is positive. Okay. Okay. So the equation is the following. For the c, we can have this one, but here we have the sort of the okay. So we say that this boundary is moving, and the dynamics of moving is given by this one. So this is really coupling through the omega t. Okay, so this is sort of the moving boundary model. Okay, so this is moving like this. So that move will change the concentration profile of this one. So this is our model. Okay. Okay. Let's numerically solve this problem. This is not so easy problem, even numerics. Okay, because you can imagine. So this is moving here and solve, and move here and solve. So like this. Okay, very tough job. Wait a second. Oh yes. And then the result the following. This is S star. This is purity. If purity is very small, then the motionless. It doesn't move. And then if S star is increasing, then there is some critical value of S star. Then velocity increasing. This is really, the pitchfork bifurcation in mathematical sense. Of course, this is numerics. We have to prove it, but this, numerics, suggests us the occurrence of pitchfork bifurcation with respect to the purity. Okay. Let's show the movie of the numerics. Okay. So this is the comfort disk here, and this is dissolved comfort concentration. But we assume this is almost circle, okay? Almost, because we assumed very slow. And what happened? So in this case, H star is very small, so just stop. So just stop here. Because you know this one, so just stop here. So not surprising, okay? But how about the case when S star is become larger? Yeah. Maybe it's better to see. Oh, sorry. Maybe here. You know, this is really far from the wall, so I said this doesn't hit, but this case is of course this is just touch with one, so you can see only this one. But in chemical point of view, just this is very important. Okay, and this is just hit and then probably moving here. Of course, in the previous slide I just explained by using 1D case, but you can imagine, okay? So like this. And for this is ES, like this, okay? But this doesn't hit. That's why the important thing, this is very important. Okay. So now, let us consider billiard problem where a slowly traveling disk moves in a rectangular domain with reflecting boundary condition. And the question is, how is the motion of the Canfor disk? Can we predict the motion? That is our problem, okay? In a mathematical way, okay? Okay, and then the strategy is the following. If the velocity is very, very slow, then one can expect that the shape of this dissolved Canfor seems to be almost radially symmetric, so like this, okay? Of course, in the previous picture, okay, but then you can imagine probably the movement or the motion of this Canfor disk is given by the point of the center, okay? So if we know the motion of P of T, then we know the movement. And this is not so easy, but we use some reduction to all these by using center manual theory. And please check this paper. A little bit complicated, but in the paper, we can precisely, explain why we have the equation for P. Okay, so this is a very simple equation. Pt equals V, Vt equals something. And V is as if the velocity. So this P is a location. And these two equations is decoupled because the equation of V is closed by itself. Okay? So, okay, this same equation, if we use this one. And the delta is given by this one. So if delta is positive, it means there's a positive, this S star is small. If this is negative, S star is bigger. Okay? And then if you can solve this equation, very simple equation, then putting here, so you can get the, the movement. But you know, this is a very simple equation, very simple equation. And then, okay, so here, same thing. And at first I have said, if W0 equals 0, this is 0, then WT always 0 by using the unique solution for anything. And if W0 is not 0, then this value is given by this one. Of course, maybe someone, just check, so. Just you calculate this one. So this is yes, that's zero. What this is very important. Okay. This is very important because this means okay, sorry. Oh, this means a sort of direction. Okay. That this means. Yes, if it is moving this way, then straight forward like this, okay? This is very important information, okay, here. And also, if delta is positive, I told you, then look at this one. Vt equals 0, becomes 0. What does it mean? This case, here, is that moving and stop. Because this is a stable. And this is unstable. Instead, we have a non-trivial solution, is given by this one. This is just moving, okay, with constant velocity here. That is so. This is in this delta. Even if some initial condition given, that's moving and stop. But in this area, moving and with asymptotically with a constant velocity. Okay, this is very simple, but we have very clear result, information. Okay, so this is just only the simple model of only the single the Kampfer disk. But we are interested in the 2 or 3. Okay.
So if you multiply V to the first equation,
yes,
and you multiply W to the second equation,
yes, we can get the yes. That is give a sort of the dynamics of velocity. You are right. Yes. Okay, so now we are interested in the interaction of the 2 toroidal disks. Okay, so like this, and this is P1, and this is P2, and the V1 this velocity. This is also another velocity here, and we assume that this distance is h, and from P1 to P2, the vector from P1 to P2 is h arrow, and E is this unit vector given by this sum. Then now, what is the equation to describe the dynamics of P1, P2, V1, V2? That's a question. Okay. Now this is in our case, it's a 2-dimensional case. This is a 2, maybe 8 unknown variable. Okay. Okay, this is the equation. Okay, I can explain. This is the same one. This is interaction part. If this is exponential, these are some constant. I don't explain, but this is sort of the decay order of the dissolved Kampfer. But now trust me, this is a constant here. And this is exponential here. This is just algebraic, 1 square root h. So if h is very large, so this is 0. This is exponential, this is okay. So it means if h is very large, that will independently move, okay? So if h is not so large, so they and they interact with each other. That each interaction is given by this sum, okay? Because this same, and this interaction part. And look at this is a sort of the root, maybe root h is the absolute value v2 minus p2 minus p1, something like that, okay? So this is a sort of theorem by using Center-Manuel theorem, but this is approximation. We have also we are higher order here, but we just neglect in this case. Okay, and this is still numerics. We solve the 8th order ODEs. Okay, and what happened? And what difference is this divides? Okay, this is okay. If this is just on the one line here, so probably you can see it like this, and here we know. Okay, but if this a little bit shifted, so we can imagine sort of oblique, reflection like this. Okay, so like this. So this the previous 8th order ODE is very nice. So let's analysis, but it's not so easy to analyze because this 8th order ODE. At most, maybe for me, at most 3 component ODE is enough. Okay. Then we think about so the reflection of the moving disk or spot, like this is the deflection and moving here. Okay. And we assume that we expect this moving here and like this. Okay. So we put here, and this is a x0. Okay. And by using the previous 8th order ODE, we can derive the equation to describe the motion with the deflection. Then suppose this is P1 and x1, x2, And this is P2, X2, Y2, and the same thing here. But in this case, we use a sort of a reflection mirror. That's why X1 and X2 is this relation. This is X1, this is minus X1. So here, okay? And Y1 and Y2 is the same. V1 and minus V2 and W1, W2. Okay, this is sort of the, relation coming from the mirror symmetry. Okay? If we use this, relation, we can reduce the 8th order ODE to 4th order ODE. Okay, for instance, this means that this is distance, okay, 8. So this means, so in this case, this x, okay, or say x1, so this is 2 times x1, okay. Okay, so this is, and then we just put in P, this is x1 and with VT, WT. Then we can have this one. So I know this is 2x is coming from the reflection, okay? And this is square root. And this is the same thing. And this is a 4th order ODE. But it is very lucky. This y does not include the 1st and 3rd, 4th. No. That's this essentially this system is 3 component ODs. We are very happy. And we get W, they put it here, then we can get Y. So we are very good because our system is finally reduced to the 3 component OD. Then probably you may do something. Okay? Okay. So it's very hard. Okay, but anyway, I have to explain. Suppose the initial condition x0, y0 is very, very large, so like this, okay? And suppose this is moving this way. Yes. Here. And V0 and W0 is given by the negative, just this is moving this way. Okay, here. And after that, what happened? And you can analyze, of course this may be homework, okay? Analyze the 3 component ODE. You can say the following. Okay, then we have a sort of the reflection. Doesn't touch with this, which means x is always positive. That is we have to prove it. But x is always positive. And only one time the velocity is changed. Okay, that is sort of the mathematical, the representation. And then eventually the velocity moving on this one, okay, and here. And this is numerical simulation. So suppose here on this here, and the t tends to infinity is moving here and coming here on this line. So if we know that this point, then and this point gives a sort of direction, or this is the reflection. Okay. Anyways, okay. Here, okay. This is given by the initial condition, and this is given by this one. So mathematically, we can say this is reflection, and if we take our initial condition here, then okay, that gives sort of the incidence angle. Then we can uniquely get the reflection angle. This is mathematical result. Okay, so and then this is sort of numerics here. This is incidence angle, and this is reflection angle. Okay, and this is 45 degrees. This is perfect reflection, but the curve is like this. So what that means is the incidence angle always bigger than this one. This is very much agreement with the experiment. Okay. 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 Now we have to move to the billiard problem. And so now we're talking about this one. Okay. But we have 2 and 3 and 4. So we think about this one, mirror reflection. And if you can do that, the final equation is a little complicated, but we finally discuss it. Give this one. Okay, and so C is okay. This L is this the Y, and this is CL. So C is a sort of ratio between the vertical and horizontal lengths. And please, trust us. Then, what we are interested in the following. If we put here, for instance, then we already know this moving here, and then if we know that this angle, then we know that this angle because of this one. Okay. And then something like this. And the question is, what is the movement? This is a mathematical question. Okay. And now I will show some numerics. Okay. Here. So this is C equal 1. So this is just square. And we solve the previous ODEs. Okay. So can you imagine something? This is almost periodic. Yes. So here. Okay, atmosphere and moving here and deflection here. Yes, and here and coming back here, like so, something like this, and finally, so like this. Okay. So it means the following: if I and you play the billiard in a different, okay, so the result is same. Okay, but anyway, this is a sort of the numerical result. Of course, we have to prove it. Okay. Now, how about this C is 1.3? This is longer. So what happened? Now is a sort of the anti-clockwise, and then clockwise. Okay, clockwise. And then anti-clockwise. So alternatively, clockwise direction and anti-clockwise is a sort of change. It's like a chaotic behavior. Okay? And so this is almost dark, but this is just a trace of the particles. So I don't know. So something like
double periodic?
Huh?
Double periodic, double.
No, this is quasi-periodic. Yeah. Finally. Yeah. Okay. So now, C3. Can you guess? Yeah. So, result is the following. Very nice periodic movement. You could see here, and so like this, or like this. Okay. So this is the same one. So at first, the square is very very nice, And then 1.3 is very complicated. And now 3 is much more simple, okay? Okay, so this is, so this axis C, okay? And this axis how many points, okay? For instance, in this area, it is like this, and this is only 1 point here. It means this is here. And then, for instance, here, this 2 is just here and here. And this 3 is like this. It's very complicated. And here is so many is like this. And this is also very much. And so it's a sort of the very cascade, depending on the C. Okay, so this is a sort of the numerical result, okay? And maybe so in your, proceedings, okay? You can read how can we get this kind of one, okay? Okay. Okay, so what should do?
The ratio square root of 2 is obtained from...
sorry.
I mean, the ratio, the x to the minus 1,
yeah.
which is obtained.
Yeah.
That ratio is obtained from experimental linearity.
I don't know. That is just coming from the mathematics. Yes.
Not from the original.
No. Okay, so mathematical problem. Okay. At first, I just said this equation, and of course, this 3-component equation, because this is, just after that, we can get this. And can we prove the reflection property? And please try to prove, to show the reflection property. So I told you, so at first, suppose the initial condition here, then you can prove the xt always positive. It means never ever touch. Second one, you have to prove the velocity is only one time change. Okay, the one time change for the v. W is almost same. Okay, only this way. But anyway, please. And second, how can we prove the existence of such a periodic motion? So it's not so easy at this moment, because this is a sort of the periodic solution.
Is it unique periodic solution?
This one?
Yeah. With stable periodic solution?
Wait a second, I forgot, but I remember. No. Depend on the but it depends on some parameters. Yes. Yeah. But in this case, it is a trivial one. So this is stable. Okay. Yeah. But okay. Sorry, I've confused. Okay. So this is very nice square region. That's why this is like this. Okay. So that's why sort of the sorry. This is unique. Okay. But if you change a little bit, okay, a little bit longer, not 1.3, but maybe 1.1, for example. So of course you can imagine something like this, okay. But in this case, this is not unique. Yeah. Maybe so in the paper, so I shall explain. Okay. So this is sort of, we have to prove the existence of the periodic solution of the 3-component OD. But probably so so this is not so easy problem. So what should I do? I did the following. Suppose this is very long. Okay, very, very long. So it is very huge vessel. Mathematically, we can think about that. So what happened? Then, okay, so maybe here, but this is very long, okay? So it means almost constant. So something like this, okay? Because, you know, so now this is like this, of course, I know. But if this is very long, this is almost touch, okay? And the information is given by the relation between the two angles. Okay? That's why our problem can reduce to the discrete dynamical system. Then, if so, we can prove it. Okay? And the property, so you can do it. But anyway, so what I'm saying is following. At first, I mean, I showed also moving boundary problem. This is very hard for us to analyze. Then we assumed that is moving very, very slow. Then we can reduce to the ODE. And if you use such ODE, we can prove the reflection property only. But we cannot prove this one. Then we just, extend this very huge vessel. And we reduce the ODE to the discrete dynamical system. Then we can prove it. So this is just mathematical, the simplification. So we have three, the levels, okay? Then we can use mathematics to understand this kind of one. Okay, so thank you. Okay.